Hello, everyone. I would like to welcome you all to today's virtual tour of NASA Glenn's Space Environments Complex located at the Neil A. Armstrong Test Facility in Sandusky. During our virtual tour, you'll hear from Bob Kowalski, the previous facility manager of the Space Environments Complex. Bob has since retired from NASA, so we will be introducing you a bit later to John Zhang, the current Space Environments Complex facility manager, who will be joining us today to talk about the facility and answer any of your questions. So I hope you enjoy this virtual tour of our Space Environments Complex, and we will now play the recording.
Hello, my name is Bob Kowalski, and I'd like to welcome you to the Space Environments Complex located at Glenn Research Center's Neil Armstrong Test Facility in Sandusky, Ohio. I'm the facility manager of the Space Environments Complex, which houses the world's largest thermal vacuum chamber, the highest capacity mechanical vibration or shaker table, and the world's most powerful, loudest acoustic test facility. We like to call it a one-stop shop for space environments testing. And because of the construction of the vacuum chamber, we also have the largest reverberant electromagnetic interference lab. I'm really looking forward to showing you around the place. So why don't we go ahead and get started. What you see here is an aerial view of the Space Environments Complex looking west. The facility was originally built in the mid-1960s to subject nuclear power and nuclear propulsion systems to space environments, mainly the vacuum and temperature extremes. So this drove the design and construction of the vacuum chamber, which we'll talk about more when we get inside. Nonetheless, testing with radioactive materials never took place. The vibration table and the acoustic chamber were added to the facility's capabilities around 2015. And the big gray building you see in front is our assembly high bay. When we get inside, you'll see that. You see the dome here of the vacuum chamber. And then on the far west side of the building is the acoustic and the vibration lab. All right, so here we are inside the assembly high bay. This huge bay is about half the size of a football field, and it's being 150 foot long, 75 foot wide, and about 90 foot high. You can see the top of the facility here is a crane that we use. It's a 25-ton crane that we use to bring our test articles in and move them around the high bay. This is where we prepare our test articles before testing. The large gray door at the far end is 50 by 50 foot long, and there are 3 full sets of railroad tracks that run through the facility, all the way through to the other side. The items you see here in white in the center is really a structure that we'll see later on in the tour, but it was the framing for temperature bars or thermal bars that we used to heat up the Orion spacecraft when it arrived here for thermal vacuum testing at the end of 2019. So let's take a look around here. So like I said, it's a pretty big building, pretty big room. And what I'm going to show you next is a video of the Orion spacecraft arriving into this facility. It will come in on a flatbed, and you'll see it laying horizontal. So this actually took about 3 days to actually complete. And now they're unpacking it. The technicians and the engineers are unpacking it. And what's going to happen next is the vehicle is going to be raised up vertically so that it can be set inside its thermal cage. I don't know if you saw that, but there are rocket engines on the bottom of that white cylinder, and that's the service module. We'll see that later on in the tour also. So now you can see the crane is preparing to lift this test article and place it on the thermal, or inside the thermal enclosure, which you see here completed with the heater bars in it. And we're going to see a couple different views of it being lifted. It was only lifted once to be placed in. And the cage is closed around it, and then it will be ready to be wheeled in or pushed on those railroad tracks into the chamber. All right, well now we're going to look inside the thermal vacuum chamber and see how big this place really is. So you can see that the railroad tracks now extend all the way through into the chamber. And it also, this view gives you an idea of how this chamber is actually constructed. It's actually a chamber within a chamber. The inner chamber is made of aluminum, that you can see here. It's less than 1 inch thick. The inside volume, which you're going to get a better picture of in a few minutes here, is about 800,000 cubic feet. It's 120 foot tall and about 100 foot in diameter. It took about approximately 2.5 million pounds of aluminum to make this chamber, and from what I understand, back when it was made in the mid 1960s, that took a fairly significant portion of the U.S. aluminum production in order to make this chamber right here. So because the chamber is so thin, like I said, it's less than an inch thick. When you pull a vacuum on the inside of that chamber, and because of the outside pressure pushing in, now that you don't have any pressure on the inside, that aluminum structure would crush like a soda can. So in order to protect that, the designers designed that large concrete dome that you see when you are looking from the outside of the building, and you can see the concrete here, the walls, to protect that chamber. So when you pull a vacuum on the chamber, you now have the concrete that's taking the majority of the delta pressure from 14.4 on the outside to very little pressure on the inside. And so the inside chamber is protected. Inside the chamber, when you have the doors closed inside the aluminum chamber, are approximately 35 tons of air. And when we pull a vacuum, we get out all but 2 grams, which is about the weight of a penny. And it takes about 8 hours to do that. A couple other interesting facts now. So what you see here is a picture of the edge of a door of the concrete door that closes to close off the concrete portion of the chamber. Now this door, you're just seeing the edge of it, is 50 by 50 foot. It weighs 5 million pounds, takes about 30 minutes to close. And when it's closed and there's no pressure on the inside of the chamber, it holds back about 6 million pounds in force, just from the outside air pressure pushing in. When Orion came here, he tested it to make sure it could hold its pressure, that it could reject the heat itself was generating, because you've got all those electronics on the inside. You want to make sure that it could actually get rid of its heat so it doesn't overheat, because when you're in space, you don't have the conduction and the convection of your air to help you cool. It's all done by radiation. So you're doing multiple things with the thermal vacuum test. Okay, like I said, the chamber is 120 foot tall. You can see how tall it is, and it's 100 foot in diameter. Maybe some of you have seen this chamber. It made its acting debut in the 2012 movie The Avengers. And this is the first 15 minutes or so of the movie was shot inside this chamber. So what you see in the center of the chamber, though, is what we call a cryo shroud. This shroud provides the background cooling to subject test articles to temperatures down to minus 255 degrees Fahrenheit, simulating temperatures that a spacecraft may see in space. So I told you earlier and showed you the thermal cage that the Orion vehicle was surrounded in prior to its being rolled into this chamber. And that provided the heat for the heat load that the spacecraft would experience. This cryo shroud provides the actual the cold background of deep space that the vehicle would see. It's all closed up in this view, but here's a picture of it when it's opened. And what you see here is there's 4 petals actually that will open up, allowing the spacecraft or whatever you are trying to test to roll in on those railroad tracks that are at the bottom of this picture. And then that is all placed in the center of this cryo shroud, and then the cryo shroud is enclosed or closed up. Like you see here, it folds around like a cylinder, and then you cover the cryo shroud with this aluminized mylar. And what that mylar does, it actually acts as a insulation, because you're trying to keep this structure cold. The walls of this chamber may be a little warmer than what you're trying to cool everything down to. So this mylar will keep the heat away from the chamber walls from radiating onto that cryo shroud. Now here's a picture of Orion. This is the vehicle you saw being prepared earlier, sitting in the center of the chamber. Now this is actually in preparation for the electromagnetic interference testing that we did. So you don't see the cage around it, but this is what it looks like while it's sitting in the chamber with those petals of that cryo shroud open. So the vehicle itself, Orion vehicle, it is the Artemis mission. So that was the Artemis 1 actual test article that was in there. It was subjected to the vacuum of space and extreme temperatures for almost 4 months to prove it was ready for flight. All right, so let's continue moving west to the facility. I will spin us around. You can see these railroad tracks do continue on to the other side of the facility, but this is what we call the vibroacoustic high bay, and it's what houses our mechanical vibration table and our reverberant acoustic lab. So let's go inside. Now we're looking back where we came from. So you can see there's a 50 by 50 foot door, and we were just standing inside the chamber right here. And this bay here is smaller than the assembly high bay where we came in. It's about 100 foot long, 70 foot wide, and about 75 foot high, and has a 30-ton crane on the top for helping move test articles around. But what we see in front of us is our mechanical vibration table, is what you see the silver ring down in front of us. This shaker table is about 19 foot in diameter and can accommodate test articles up to 75,000 pounds, making it the highest capacity shaker table in the world. And they can take those test articles, they can shake them from 5 to 150 times per second at forces in the vertical direction, that's up and down, of 1.25 times the force of gravity, and horizontally equal to the force of gravity. So that takes a lot of energy in order to move something that heavy at those frequencies. So why we do this is to make sure that spacecraft or whatever you're testing can withstand the shaking environment of a launch on a rocket. So things get, as you've seen maybe videos of in movies of how wild it is to be inside the capsule of a rocket while it's taking off. Well, you got to make sure that that capsule can, and all electronics and everything, that can withstand that shaking. So in order to do that, we have an 1,800 horsepower hydraulic system that drives 16 vertical actuators up and down in order to shake the table up and down, and 4 horizontal actuators to shake the table sideways. Now these actuators, you don't want the actuators to be sitting on something that's unstable, so they're actually secured to what we call a reaction mass, which is just something that's really, really heavy. And as a matter of fact, this table is anchored to about 4.6 million pounds, which is really a lot of concrete and steel that's tied directly to the bedrock. So this assures that the table and the test article move, and that's it. The vertical actuators, when they're moving, supply a dynamic force of about 480,000 pounds. I'm going to show you a real quick video here of what it looks like underneath this table, and so you can get an idea of what these actuators look like. And so you'll see a technician walking underneath the table, and you can see these black vertical columns. That's the actuators. So those are the things that make the table move up and down. And there's 16 of those that are underneath the table. Now, when we first got into the facility, we showed you the Orion vehicle coming in with its crew capsule and its service module. Well, here's a picture of the service module being lowered into the vibration table. This vehicle itself weighs approximately 78,000 pounds. And so this is what it looked like while it was being lowered onto the system. And then I'm going to show you a quick video of this actually being shaken from about 5 to 150 times per second. What you see on top is the blue oil derrick looking structure is the simulator for the crew capsule. The crew capsule itself was not actually shaken as part of this test, but you can see the whole structure shaking. You can see the bottom of this crew capsule or the service module with the rocket engines on there. And they needed to make sure that all those systems could withstand the vibrations of launch. Okay, so now we're going to turn our attention to the Reverberant Acoustic Facility, or RADF, at the far west end of the facility. All right. This facility is the most powerful or loudest of its kind in the world, and it's capable of producing sound up to 163 decibels. In comparison, the sound of a jet engine taking off from about 200 feet away is 130 decibels, and the threshold of pain in your ears is about 140 decibels. The sound is generated by 36 horns that you see here on this wall. And these horns are rated for different frequencies, and that's why they're different sizes. And we generate sound from about 25 hertz up to 10,000 hertz. Just as a comparison, really good home speakers really can deliver probably about 8 watts of power. These horns can deliver 1.5 million watts of power into the chamber. is that's about the same as 20 jumbo jet engines, for instance. So there's a lot of energy and a lot of power going into this facility. So the chamber measures approximately 50 foot by about 57 foot high. And an interesting thing to note here is that you'll see in the top of the chamber is a slot. And that slot is used for bringing in test articles with our crane and allowing the crane hoist to come through that slot and then lower your test article down onto its table, then come back up, and then on top of the chamber there's a big plug that is raised in order to help seal off the chamber, so that crane will lift the plug and set it down into that slot. Now it's very important that this chamber can be very, we'll call it acoustically active or very reverberant. So we have to seal it up, and as I told you, there's a slot on the top of the roof, there's a door at the far end here that closes, and then you can see there's a kind of a door here that will swing shut, as well as a door on this side that rolls closed. So when you seal it all up, the echoes in here are incredible. It takes about 20 seconds for sound to die down. So if you clap your hands or shout, your sound will reverberate in that room for about 20 seconds. And it's really hard to hold a conversation in there when the doors are closed, because you start talking up on top of yourself. And you do that because you want the sound to be equally distributed on whatever you're testing. As you notice, there's horns only on one side of the room here. These holes on top here are actually vents, and we'll talk about that in a second. But the sound is generated just on one wall. And because this chamber is so acoustic, after the horns get started, the whole room is bathed in this acoustic sound, and all sides of your test article get completely bathed into the sounds. What you see here is not a flying saucer. It's actually just a table that we use to set test articles on. But what a test article does look like when it is installed in here is what you see here on that white structure. This is a covering that goes on top of the Orion crew capsule. It's called an ogive. Well, basically what it does is it protects the crew capsule from the exhaust of the launch abort system if it needed to go off. And while you're testing it, is you want to make sure that your spacecraft and whatever structure that you're building that you want to test can survive the launch of getting into space. So you have the sound of your rockets going off for one thing, and you also have the sound generated by the rocket going through the atmosphere into space. Until it gets into the vacuum of space, you're going through basically the atmosphere and the air, and that creates a lot of sound on your vehicle. So these horns use nitrogen gas in order to generate the sound, and before we test, we purge the inside of this chamber with nitrogen. So since these these horns use nitrogen, we bathe the inside of this chamber with nitrogen so nobody could be in there. And this video I'm going to show you is a quick video. Actually goes through this large horn right here into the back room towards the business end of the horn, we'll call it. So you're going to go inside. This is a 25 hertz horn. It's the lowest frequency horn that we have. And you'll notice that the horn itself is bent as you go through. It's not straight, it's curved. And the reason is because this building that this acoustic chamber was built in had defined outside walls, and those walls were too narrow for this horn to fit straight, to have a straight horn. So it had to be curved in order to get inside the room that was already there. So what you see here now is where the sound actually comes from. This pipe on top will bring in nitrogen gas at a high velocity, and it will pass that gas in this device here past a piston moving at the frequency that you want the horn to generate the noise at. And then that gas is passed through the horn where it's amplified to the loud sound that we can generate. And that is how this works, is similar to how your own body would use to make a sound with a horn. Well, that completes the tour of our Space Environments Complex. I hope you got an understanding of the unique capabilities of this facility and what is truly a one-stop shop for space environments testing.
There's some pretty cool stuff there. I hope everybody was thinking of their questions. John Zhang. It looks like he is on now. So if you would like to introduce yourself and add anything before we start with questions, please go ahead.
Okay, well, I'm the current facility manager here at the Space Environments Complex at the Neil A. Armstrong Test Facility in Sandusky, Ohio. I've been around ATF here since 2006, and previous to my current appointment, I was the test manager here. So, open to any questions that may be present.
So during the video, they mentioned that they had testing for about 4 months or so. Does that require a 24/7 presence from employees to kind of maintain the testing? And if so, at night, how many people are required to be there?
For acoustic and the sound vibe that you saw in the video, we typically don't run 24/7. We are able to maintain a roughly about 10 to 11 person staff per shift to run the facility on the NASA, GRC, ATF, SEC side for this facility. There was probably an equal amount of our counterparts from the Orion program, working vehicle operations, looking at the thermal conditions, providing direction for us as a facility. We really provide the environment for the vehicles to test in, and then normally the customer will then operate their hardware within. So we're really operating the facility. In that case, yeah, we do operate 24/7 typically for thermal vac. Not so much for some of our other capabilities. They're much shorter tests. An acoustic test and a vibration test, they usually run in the minutes where they're exposed to the environment. A thermal vac, if you think about it, we're trying to get something hot and then cold. Those are very slow processes.
Why did they choose to build the chamber out of aluminum?
The facility was actually built for items that could produce some radiation, and material wise, aluminum provides a very good material for that purpose. Stainless steel, if neutrons were to come off of whatever the test article may have been, it could render the facility kind of useless for several years to many years, where aluminum, the half-life of the products that could be developed during the exposure to highly energetic neutrons, it would be very short, within hours or minutes in most cases.
Do you do any repairs of rockets or just perform the testing in Sandusky?
When you say rockets, we are primarily testing components on spacecraft. So we are testing anything from the fairings, which sit on top of the rocket, which would encapsulate a payload as it's delivered into orbit, to the Orion capsule, which is going to fly crew. Um, our facility is not meant for propulsion type testing, so we do just environmental space testing on those kind of components.
Does the SEC facility require continuous maintenance and repair, especially after the vibration testing?
Well, that's a good question. Certainly, we require a continuous maintenance of a facility. Most of the facility systems here were built in '69, and a lot of the equipment, I'd say a large portion of the vacuum equipment is still original, where we've been refurbishing as needed. Vibration testing, believe it or not, because of the large mass that it sits on, doesn't do any damage to the rest of the facility. We do have to do more maintenance as we add capabilities to the facility. So the hydraulic system has to be maintained that supplies the hydraulics to cause those actuators to move in and out, as we cause the vibration on the table. And then the same holds true for the acoustic testing, where we run hydraulics through an actuator that essentially moves back and forth at a very high frequency. You think of somebody operating a horn. We operate that to create the frequency condition, and supply the sound level to the chamber. So all of that has to be maintained.
All right, our next question is, do you have an on-site emergency response team?
We do not. We depend on the local emergency response teams. We're in Sandusky, Ohio. We actually sit in the township known as Perkins, and they supply us with first response as needed. So the guards, we have an 24/7 on-site guard team. And if someone were to dial 911 from any one of the internal phones here, it would be directed to them, and then they would direct it to the first response team.
Looks like there's a student who would like to know if you can tell us how long it takes for a rocket to actually get to outer space from Earth.
So I don't know if I'm wholly qualified to answer that question, since I'm not that type of engineer. Um, I would say that it's in the minutes. If you've watched any of the recent SpaceX launches and past Saturn launches, shuttle launches, it takes several minutes to leave, and it depends on where you consider the what is outer space. So above 100,000 feet above the Earth's surface is typically where we start to consider that to be at the edge of outer space. So, or as we get into low Earth orbit, which is primarily where we've been going recently, to the ISS with a lot of our crewed missions. So
Are there any other tests done there that are not NASA devices, such as SpaceX, etc.?
very much so. I mean, we are not strictly testing NASA hardware. We are testing SpaceX hardware. We are testing Blue Origin hardware right now. So we are pretty active with our commercial entities. And so they request test services from NASA and from our unique facilities. And a lot of times it's supporting NASA missions pertaining to SpaceX. Sometimes not so much. If everybody's familiar with the Starlink system that SpaceX is putting out there for global internet, we've done a lot of testing with them on those components. So we are kind of a mixed bag.
You said the facility was built in 1969, which is the same year Apollo 11 went to the moon. Was anything from that mission tested in the SEC?
That would be yeah, there would be nothing that was tested here from those missions. Again, I think we were more tied into the maybe NERVA program, which would have been the nuclear rocket.
So, another question, what advice would you give to students who may want to work at NASA someday?
Obviously, we're heavy in the engineering field, so folks that are going to have a background in really any of the engineering fields, and then getting in the door in one of the internship opportunities, whether it be the pathways, um, or the LRSIP. I think it used to be called LRSIP programs. Getting your foot in the door there creates relationships and gives you an idea on what opportunities there are there. Obviously, maintaining a good GPA and and uh, and graduating, I think, is key. But I think one of the things is to kind of press on those opportunities as they are available.
You said most of the testing items were built in 1969. If you could get one piece of new technology to help you do your job better, what would it be?
That's a very good question. Most of the new hardware here, as Bob mentioned, the vibroacoustic side of the house it was built and implemented in 2015. So it has logic controllers, computer-based systems to run it. We're slowly bringing our vacuum systems up to that level. So I would say if I could swap anything, it would be the old relay-driven, electronics for operating our vacuum system to a more modern logic-controlled system where we would have, a little bit more control. We have, because the facility is so large, we have several areas that we run that are remote from our primary control room that we have to staff during a vacuum test, and particularly a thermal vacuum test. So that would be one item that I certainly am, proposing in the future for an upgrade.
Okay, and we got another question. Does the SEC have a busy test schedule, and which section is used the most often?
So a couple years ago, I would have said RADIF, the acoustic test side, but we do have a busy test schedule. So I mentioned Blue Origin's been here. They are actually doing a vacuum only test to separate a fairing here. I think there's if you follow their Twitter page or Facebook page, they probably have a video here there where they separated their fairings. within our chamber, and they've done it twice. They've just finished up their last test. We will actually get the Orion capsule back after it launches on SLS and it lands to finish up its acceptance testing in the acoustic chamber here. We're also we're also looking at doing some testing for the Halo, which would be part of the Gateway program, which would be a lunar station. So there's two initial modules. One's the crew module, which would be Halo, and then also we're looking at all kinds of thermal vac, sign, vibe, and acoustic tests for the human landing systems that are being solicited by NASA here in the next couple of years as well. So we have I think we receive probably about 25 inquiries a year, and out of that we get maybe 2 or 3 tests a year. So we're in that 2 or 3 tests. There's several months, 5 to 6 months of activity.
In your opinion, what has been the most exciting thing to happen at the SEC?
It's been several years since we had a major component of a crewed mission, and Orion coming here and testing along with the SpaceX Dragon capsule a couple years earlier has positioned us to kind of be a test bed for major crewed missions and really stakeholders and the whole process of our position to get to the moon and beyond. So just the overall uniqueness and being able to participate in that process gives us a level of pride, I think, that maybe we didn't have as much before because we weren't essentially testing a lot of those type of systems here.
Have any findings from your testing ever resulted in any landmark improvements in spaceflight?
Certainly, and I could roll off a list. It's certainly cheaper to test on the ground than it is in flight, just due to the cost of launches and the type of equipment you've got to haul, instrumentation. I can't mention it specifically. A lot of this is proprietary, but we've had customers who have tested components that after initial testing have have found significant flaws that were corrected for subsequent tested that would have cost their programs, the taxpayers, millions of dollars if not caught here.
So it looks like that is all of our questions. We hope that you enjoyed today's virtual tour of the Space Environments Complex. And before we conclude the event, I would also like to provide you with some additional resources. I encourage all of you to visit our website, www.nasa.gov/Glenn, to discover more about Glenn's mission and research. You can also view additional self-guided virtual tours by going to www.nasa.gov/Glenn virtual tours. And our next virtual public tour is scheduled for September 14th at 1 p.m., where we will explore our ballistic impact laboratory. To register for that, you can visit www.nasa.gov/Glenn NASA Glenn Tours. And did you guys all know that NASA Glenn's official visitor center is located at the Great Lakes Science Center? You can visit www.greatscience.com to learn more. And educators and students or anyone else interested in our STEM resources and educational opportunities can learn more at www.nasa.gov/centers/Glenn/STEM. And in the coming years, NASA will be landing the first woman and first person of color on the moon, using innovative technologies to explore more of the lunar surface than ever before. To learn more about the Artemis missions, you can visit www.nasa.gov/whatisartemis. And we also have a quick video for you guys about the Artemis missions.
We are going. The history of this agency is marked with broken barriers, once viewed as impossible, with science fiction turned reality, with innovations that have spun industries all their own, and with demonstrations of peace for all humankind.
We We soar in the skies of our home planet. We maintain a human presence just outside of gravity, and we touch points all across the solar system and beyond. We're going back to the moon, and this is why.
The moon is a treasure trove of science.
It holds opportunities for us to make discoveries about our home planet, about our sun,
and about our solar system.
The wealth of knowledge to be gleaned from the moon will inspire a new generation of thought and action.
Without fail, every major program and mission NASA has invested in has led to technologies and capabilities that have shaped our culture.
The breakthroughs of the Artemis era will define our generation and the generations to follow.
The tens of thousands of jobs associated with propelling us to the moon today are just the beginning of a lunar economy that will see hundreds of thousands of new jobs develop around the world.
This is not an ambition of one entity or one country. The exploration of the moon is a shared effort,
woven together by a desire for the greater good.
Why the moon? Because the missions of tomorrow will be sparked by the accomplishments of the Artemis generation today.
Because the ambition to go has already begun.
And because Mars is calling. We need to learn what it takes to establish community on another cosmic shore. So let's camp close before pushing out.
And so, we go to the moon now, not as a series of isolated missions, but to build a community on and around the moon capable of proving how to live on other worlds.
We'll use the lessons from more than 50 years of peaceful exploration to send a new generation to the lunar surface to stay.
We will anchor our efforts on the lunar South Pole to establish the Artemis Base Camp,
positioning us for long-term science and exploration of the lunar surface.
We will prove what it takes to assemble a complex ship in deep space.
We will perfect ascending down to and returning from a distant surface.
We will learn how humans can survive and thrive in a partial gravity environment.
With improved spacesuit designs, mobile habitats, and with reconnaissance robots pre-positioning and relocating supplies.
We will learn how to utilize the resources we find on these other worlds, starting with finding water ice and purifying it to drinkable water.
And refining that into hydrogen for fuel and oxygen to breathe.
We will establish fission power plants on the surface of the moon, capable of supporting a growing community of efforts.
And we will expand the logistics supply chain
to enable commercial and international partners
to resupply and refuel deep space outposts.
None of this is simple or easy, but nothing in our history ever has been.
The Eagle has landed. You got a bunch of guys about to turn blue. We're breathing again. Thanks a lot.
This kind of continuous lunar presence is a natural extension of all that we've learned in low Earth orbit. And what we will accomplish there will ensure the monumental missions to Mars are within reach. As we ready the launch of the first Artemis mission, and as commercial companies ready their lunar landers for the first private payload deliveries, we have already begun to take the next step.
NASA recently launched its First Woman graphic novel and interactive experiences. First Woman tells the fictional tale of Callie Rodriguez, the first woman to explore the moon. Through a series of graphic novels and digital platforms, First Woman aims to capture our attention and unite the next generation of explorers who will return to the moon. And to read First Woman, you can either use the QR code that's on your screen or visit www.nasa.gov/specials/CallieFirst. Again, I would like to thank all of you for attending today's virtual tour of the Space Environments Complex and for your continued interest in NASA. You can keep checking our site, www.nasa.gov/NASA Glenn Tours, for any upcoming virtual tours. Thank you again and have a great rest of your day.